Section 7.2 is volumes, and there'll be two methods for finding these volumes. It'll be volumes by slabs and volumes by solids of rotation. And we'll see examples of each. We'll start with volumes by slabs, and then we'll work into volumes of solids of revolution. So our rule here is let S be a solid that lies between x equals A and x equals B. If the cross-sectional area of S in cross-sectional slices, we'll have a look at that down in the picture below in a moment, and the plane perpendicular to the x-axis is given by area of x. So each cross-sectional area of S is A of x, and A of x is an integrable function. Then the volume of S is given by this integral here, and I'll skip from V to the integral formula. So overall, the objective is to find a function A of x that represents the cross-sectional area of a cross-section at the value x. And then you can sum all of those up through the integral from A to B. And if that describes your solid of revolution, then you've got the volume of S solid. So in between, we've got this limit of a sum of areas, and that's an approximation. Without the limit involved, that's an approximation. With the limit, it is exact as we have it. But let's imagine we've got a curve y equals f of x. Okay, so let's see where this formula comes from. We rotate it about the x-axis. So that forms a symmetric looking solid of revolution, right? This thing rotates out of the page and it forms this sort of maybe vase-like looking solid right here. And we're interested in the region of it between A and B. So we form this sort of cylindrical looking solid. It's got circular cross sections to it, and that's going to be a key thing to notice. Any solid of revolution has circular cross sections, so we're going to use this quite a bit in section 7.2. Now, if we wanted to calculate the volume of this solid that we've got here, we might consider little cylindrical segments of it. In other words, these little discs. So this region right here is a disc. It's a solid disc with width delta x. It's got a height or a radius of yi, and yi is actually the value of the function. So it's f of xi, right? So we see over here in a formula, this is happening. Yi is becoming f of xi. Now let's talk about what's going on in that formula. Maybe before we make that substitution, we can calculate the volume of this disk. It's really just the volume of a cylinder, right? Which is the height of the cylinder, which is in this case delta x, which is really the width as we're seeing it, and then times the radius yi squared times pi. So first, let's note the area is just yi squared pi, the radius squared times pi. So we get the area a sub I, and then to find the volume of that, we multiply by delta x, and that's our thickness, and we've got an the volume of this segment right here. Now we know that this segment, just like an approximating rectangle, is going to miss a little bit on the curve. We're going to have a little bit of error. It's going to overlap or it's going to underlap in some sense from that curve, and we're not going to have exactly what we need if we just did finitely many calculations for these disks and added them all up. So what we say first is that if we sum up n of these, pi times yi squared, which is f of x I squared, times the thickness delta x, then we're adding up the volume of n such approximating disks, right? If we take the limit as n goes to infinity, in other words, take infinitely many disks of shrinking size, then we'll get the integral pi f of x squared dx between a and b. Okay, so this limiting process gives us this integral, and this is exactly where the volume integral comes from. Now, in our case, a of x doesn't have to be pi f of x quantity squared. That's a nice rule to use for solids of revolution. But if we have solids of just slabs, which we'll see later, we just remember that pi f of x can generally be a of x, and a of x might have to be determined to be a different function than what this is, and it's really based on what kind of solid we're looking at overall. So again, to recap what the goal is, we don't need to know that, we don't need to remember the derivation, but seeing it helps us understand what we're doing in this section. The goal is to find an area function that represents the cross-sectional area at any x value between a and b, and then we can plug that area function into an integral between a to b, and we've got the volume of our solid that we're interested in. So let's have a look at our first example. Some of these will be examples in the textbook, some will be exercises, but all are useful. So we've got some steps above to sort of outline what the process is. Students can choose to follow that or not. The textbook, I think, uses a similar set of steps. I'll just use the natural organic process as I work through these and describe what I'm doing. They ask us to find the volume of a sphere of radius r. In other words, they're asking us to prove the formula for the volume of a sphere of radius r. If you already know it, then we're proving that formula is indeed true. So what I draw first is an x and y axis, and then I draw a sphere centered at the origin of this x and y axis, just to simplify the work that we're going to do here. Now we say that the sphere has a radius r, so we'll mark that somewhere. Okay, the sphere has a distance from its center to its boundary layer of radius r. We want to find the volume contained within this sphere. So we set this up knowing that we will likely use either a slab situation, which is what we're going to use in this case, or we could use a rotational version of this. I'll let the student pursue the rotational or the solid of revolution version of this. It's nice to see this in terms of slabs because that's the harder version. So, and it's the more general version as well. So what we need to realize, we need to find for any x value, we need to find a function a of x, which represents cross-sectional areas of whatever these regions are. Well, when we slice a disk into the page, or sorry, slice a sphere into the page as we have here, we form this disk that I've highlighted, right, with some little bit of a thickness to it. That'll be dx in our integral, so we can just ignore that. But we know that for an x value right here, we have a point xy that's on this sphere. If it's on this sphere, it's got radius. It's also on the circle that we see projected onto the xy plane. So we know it satisfies r squared equals x squared plus y squared. Okay, so what I'm seeing here is a right triangle, r squared, x squared plus y squared, right? And then we've got exactly this triangle right here, r, x, and y, and we know they satisfy the Pythagorean theorem. And now we can start to describe what's going on, because after all, we look at this circular cross-section and realize to find the area, the cross-sectional area of that, it's just pi y squared. Now the problem is our thickness is dx, right? So we'd have a of y with a dx. We can't integrate y with respect to x in any useful way here, so we need to convert that to a of x. So the process, we realize, okay, area is pi times the radius squared, which turns out to be y squared, right, as we saw right here. And then we realize, okay, this right triangle gives me the information I need to sub out y squared for r squared minus x squared. R is fixed, that's given to us in the problem, it's some constant. So we can leave it as is, we're comfortable with that. Now our area function, a of x, is given by this, pi r squared minus x squared. We're integrating from negative r to r, that's going from here to here, left to right, to pick up all such cross-sectional areas. And when we're done, we end up with 4/3 pi r cubed. The rest of that is just a polynomial integral. Remember that r is just a constant, so when we integrate it, r just stays what it is. It just remains as r squared, but we evaluate at negative r and r. When we combine all our like terms, we arrive at our volume of a sphere. So we've used volumes by slabs to prove the formula for the volume of a sphere. So again, though, like I mentioned, we could use a rotational method. We could rotate about the x-axis and use something similar to what we described on the previous page and what we'll do in other problems. But this is one example of a slab problem. Let's see a volume by slabs where we can't use rotation. So this problem asks us to find the volume of a square base pyramid with height h and base length b. Okay, so base length b, it looks like I've accidentally used L here, quite possibly. L is what I've got written here. So that might have swapped out. So we'll just, I'll make a note of that right here. Base length L, old notation. And so now we're dealing with L, and then it's got a height h. So I've written this so that we can work with it on the x-axis. Of course, when people think of a pyramid, they might actually stand the base here, this, and point it upward, something that would seem like a natural way to draw it, which is just fine. It's just you're going to have to integrate along the y-axis, and you'll see why, because in this case, we're thinking of slabs which have similar shapes to other slabs next to them, right? So if we slice this pyramid into the page perpendicular to the x-axis, we're always going to get squares out of this. And that's what we want. We want a function we can rely on. We want a of x to always have the same formula for what its cross-sectional area is. If this thing were standing up and we still wanted to slice it this way on the x-axis, well then, without actually drawing that, we'd be slicing like this, which are also squares, but they might be harder to calculate. I think this is easier to see what these squares look like the way we've got it. So anyway, it's always a good idea to draw one characteristic cross member. Okay, and there it is. This is our cross-sectional slab. This will help us determine what's going on in this problem. Okay, so let's think of a line that passes through the origin and makes up this surface of this pyramid right here, right? Makes up this boundary of it. We know that a point xy is on that line, and that's where this slab occurs. So that's our general point xy. Some things that we know is that this point, also on our line between 0, 0 and xy, is h, the height of this pyramid, which is this distance, comma L over 2, which is half of its length, its base length, right? Which makes sense because the full length would double that to L. So we have h, L over 2 is a point on our line that is known from values that are given, and we have 0, 0. We have 2 points on this line that we know. We can determine a formula for this line, and that's exactly what we'll want to do through y equals mx plus b, right? Or point slope form. Now, let's move over and think a little bit more about it. Why would we want to know that? Well, we need to be able to find the area of this slab, just as in the previous problem. So the area of a square is the side length squared. Well, this is a value of y for this square. So in total, s is 2y. We have that written here. S is 2y. And then the area in terms of y is 2y quantity squared, which is 4y squared. Now the problem is this: we're slicing on the x-axis, so we have dx. Our thickness is dx. Okay, so we need this in terms of x. So the reason we would go to this line is because we need to convert 4y squared into something in terms of x, and we can do that through the line that passes through these 2 points, 0, 0 and h L over 2. Okay, so we sort of knew that we were going to want to set this up from the beginning. We had an instinct that we'd want to be able to solve y in terms of x or vice versa. But the motivation for that, possibly we would really see this first, is that we know we can get the area of this square, but we're getting it in the wrong variable. We need to convert through some kind of geometric relation. So forming the line that passes through these 2 points, the slope is the y minus the y value here, so L over 2 minus 0, over the run, which is h over 0, or sorry, h minus 0. And L over 2 minus 0 over h minus 0 is L over 2h. And we end up with this. Its y-intercept, luckily, we see is 0. So the y-intercept b is 0. So the slope of our line is given by y equals L over 2h x. And now we know exactly how to replace y in this formula. It's L over 2h x quantity squared. So once we put all that together, remembering that L squared and H squared are just constants, we can write our integral out, starting with that slab area formula, cross-sectional area A of X. We've got that as a function in terms of X. These guys are constants, so we just factor them out of the integral, and power rule, and we work to get the volume as 1/3 L squared H. A pretty straightforward integral. Of course, the harder part is the setup. So there might be other ways to think about this problem, but one way that there's not that might be tempting is to assume that there's any sort of angle measure going on here, right? This is not guaranteed to be 45 degrees or 90 degrees or something like that unless the problem states otherwise. This problem is pretty clear about it. It just says that the base length is L, or B accidentally, but I meant to say L, and that the height is H. We know nothing else about it, so don't assume geometry that's not there. Okay, so be careful with that. So that's one of our more general slab volume problems. The remaining examples in these notes will complete in the subsequent video, and those are all going to be solids of revolution. They're a little bit more straightforward and a little bit more formulaic, but they're not quite as general as these volumes by slabs. So we'll see those in the next video.